Good morning, or afternoon, or evening, or whenever you are watching this. I want to continue on with looking at the atom and electrons and where they're placed. And so the last lesson you had was thinking about waves and electrons being either waves or particles, and I had you do some calculations with that. And that's kind of getting into this thing called the quantum theory. So the quantum theory essentially says that electrons are kind of in this space, and they aren't really just circling in a nice circle. They kind of have this probability. They're in this area or region where they just kind of hang out, and we use the wave calculations to figure out where they are. And so I want to transition back to regular chemistry, what we did with kind of the amount of energy it takes to pluck away an electron. Let me shut this. That's a little. So last year we looked at this thing called ionization energy, or the amount of energy it takes to pluck away an electron, and we saw for certain elements. Let's say I have sodium here. Sodium's first electron, it takes this much energy to remove it, but then there's this big jump between the first and second electrons. And same thing with, if I look at sodium here, sodium has, we learned that it's got in the first column, so it has one outside electron. And this one outside electron is here. And then these are what we call the inner electrons. Same thing with lithium. Lithium has this 520 with this much energy, but then there's a big jump. And we saw that this one's a little higher than this one here. And so what does that mean in terms of where that electron is? Well, remember, when things are closer to the nucleus, it's harder to pull them away. And so it's got one outside electron, but it's a little closer. And then you pluck that away, and then the next electron is really hard to remove. So this also has one outside electron, but it is closer in. And same with, look at some other elements. Beryllium. Beryllium's got 1, 2, and then this big jump. Well, beryllium is here, and it's got 1, 2. So you pull those two electrons away, and then all of a sudden, there's this massive jump between the second and the third. And aluminum is here. There's this big jump right here. 1, 2, 3. Well, aluminum is right here on the periodic table. It's not 13 electrons. It's only 3 outer electrons, so 3A. It's in column 13 or column 3A. And so it's got 1, 2, 3 outside electrons. And we see it pulls away, and then bam, there's this big jump. And so we have an inside shell. And so that's what the first thing we did was just kind of looked at how many outer electrons there are, and then the inside. And so what I want to do is have you look at some trends in the amount of energy it takes just to remove that one outside electron. So we know things have outer electrons, and I just want to focus on the first outer electron now. And if I look at the periodic table, so I have H is hydrogen. It's the first one right here. Helium is this one right here. And if I look at the trends of how easy it is to remove that first outer electron, what do we notice? What do you notice in terms of the amount of energy it takes for the first two elements here? And if I look at the next row, so this is lithium down here. If I look at this row right here, what do you notice with the amount of energy it takes to remove that first electron? It doesn't just increase, this way. So what do you notice in terms of the patterns? Okay. And then the same thing with the next row. The next row, what do you notice with those patterns? And so jot down what you see happening in those rows. And then when we return, we will kind of take a closer look at what's going on. what you should have seen, hopefully you did the analysis and looked at different patterns, and what you should have seen is the following. The energy, the amount of energy it takes to remove that first electron, it goes up. And there's this big jump from hydrogen to helium. So that's a big jump. And then it is a big drop. So we drop down from here all the way down to here. And then that goes from helium down to lithium. Then it starts rising again. So as you go left to right on the periodic table, it starts rising, rising, rising. And then we have this another big drop, and we go down to from neon to sodium, and so on. And what's happening, and I think a lot of you, kind of realizing this, is that every time we drop down a row on the periodic table, so if I go to the first row, these are really high energy to remove that electron. And then we drop down to another row, it is a lot lower energy, and that means that the electrons are farther away. So every time we go down a row in the periodic table, we say that the electrons are a little further away. It's in a different shell, or what we're going to call in AP Chem the energy level. And that's described by this first thing here. Is called the principal quantum number. So the principal quantum number tells us that it's the number n, lowercase n. And if I have the outermost electrons in the first row, so for hydrogen and helium, this is principal quantum number 1. So n equals 1 for these two electrons, these two elements. And then as we drop down a row, well, this is now another set of electrons. And so that's a little further away, and that is in principal quantum number 2. So the second energy level. So from here, these outermost electrons are in n equals 2. And so on. If I go to the third row, this is n equals 3. Okay, so starting at sodium going to argon, n equals 3. Now, that describes how far away the electrons are. Something a little weird happens with these electrons, with this here. I'll tell you about that in a little bit. But what you need to know now is mainly n equals 1 is the closest, n equals 2, next closest, n equals 3, and so on. As we get further down the periodic table, the principal quantum number increases. What you also may have noticed is there's a trend in, if I look at the second row of the periodic table, there's these little bumps and dips along the way. And so if I go lithium, beryllium, these increase, but then we have a little dip in energy between beryllium and boron. And as I go up here, there's another little dip, another little dip. So these first two elements here, sorry, can't see that anymore, but lithium and beryllium, we have this little dip here between beryllium and boron. Same here, we have sodium and magnesium, it goes up, but then we have another little dip right here. And then, this is a big dip. So there's actual sub-levels within the principal levels. And we're going to describe this as something called the angular momentum, or azimuthal quantum number, and that's going to be the letter L. As I was saying, we have the azimuthal quantum numbers. When the azimuthal quantum number is 0, it shows what shape the orbital is that the electrons can be in. So remember, electrons can be in this space or this area, and when L is 0, that tells us that the electrons can be in a spherically shaped orbital. So there's only one kind of s orbital. It's spherical shape. And for every quantum number, every principal quantum number, there is a spherical shaped orbital. So for instance, if energy level is 1, there's a 1s orbital. Remember, the first two elements are in the first row, so they're the closest. There's a 1s orbital, so that's what this one is here. If I go a little further out, the 2s is a little further out. So 2s is a spherical shaped orbital a little further away. So the next 2 electrons for lithium and beryllium go in this 2s orbital. And then if I go even further out, sodium and magnesium right here, this is 3s. Okay, so every time I go down a principal quantum number, I get further and further away, and 2 electrons can be held in this spherically shaped orbital. Now, you're saying, well, this row here, the second row, has 2 electrons here for the 2s suborbital, but I have all these other electrons. They need to go somewhere, and they can't fit in the 2s orbital because it can only hold 2 electrons. And that's where the next set of orbitals comes in. So when it turns out, as you keep going down the periodic table, as you keep increasing the principal quantum number, you actually increase the number of types of orbitals that are available that electrons can go in. So in the second row, we have the 2s orbital, but we also now have the principal quantum, the azimuthal quantum number can now change to L equals 1 also. So it can be L equals 0 for the 2s orbital, or L equals 1 for the 2p orbital. So the p orbital is a dumbbell-shaped orbital, looks like this. And there's actually 3 types of p orbitals, and they're in different directions on the Cartesian plane, or the 3-dimensional plane. And so these next 6 electrons here, from boron through neon, they go into the 2p orbital. So we have 2p, 3 different kinds. Remember, there's 3 different kinds. Each one can have 2 electrons. So you can see how many electrons can fit in here. Next, go in the next row, 3p. So from aluminum to argon, aluminum here to argon here. All these things right here. Okay, so another 3p orbitals. 4p is over here through krypton. But then you notice like there's this large group of elements here, and they need to go somewhere. So the final kind of orbital I want to talk about today is called the d orbital. You go down to level 3 on the periodic table, and another set of orbitals opens up. And this is called a d orbital. So when L equals 2, there's actually 5 different kinds of d orbitals. They're all funky shaped, but 5 d orbitals. And this starts here. Okay, so we go from here to here, all the way to zinc. And that starts at 3d. So 3d is the first place we saw d orbitals. So remember, 1s in the first row, 2s and 2p in the second row, 3s, 3p, and 3d. 3d is over here. And so I'm going to have some questions that deal with that. Try as best as you can with those.